Bismillahirrahmanirrahim. Rabbi shrah li sadri wa yassir li amri wa halul uqdatan min lisani yafqahu qawli. In the name of Allah, the most beneficent and merciful. Today's lecture is about modulus of subgrade reaction. Uh, this modulus of subgrade reaction is used as an input in the design of rigid pavements, be it highway, port pavement, or an airport pavement. Uh, the objective of this lecture is to apprise the students how this um, subgrade reaction is calculated, what are the test protocols, and how it is uh, similar to or similar to CBR soil test. I am Professor ADNAN. Just go with the conventional definition. Uh, Now, if you want to know the modulus of subreaction, it can be defined as the reaction pressure sustained by the soil sample under a rigid plate of standard diameter per unit settlement measured at a specified pressure or settlement. Uh, Let's see how this simulates the actual field condition. Now, we all know that whenever the vehicle passes, it applied a load, it transfer a load uh, through its tire to the pavement. Since this pavement, uh, this reaction is needed for a rigid pavement, so that's why we say there is a rigid plate uh, of standard diameter that is going to take the load, and this load, whatever is the load that causes a unit settlement uh, at a given tire pressure, is known as the modulus of subgrade reaction. Uh, if you look at this diagram, you can see a wheel load is applied vertically to the surface of the pavement, and it is distributed in a uniform manner. So you can say this is a rigid plate from which the load is transferred, and to there small deflection is created, and in order to compensate this deflection, or another way to pull that deflection back, these reactions occur. So we can say to this action, there is a reaction from the soil. Obviously, a very good soil will have more P value as compared to a weak soil. Or if a wheel load is, high, then we may need a thicker rigid plate. If you look at mathematically, this reaction is proportional to the deflection. And if you just remove this proportional sign, then this reaction, this proportional signs can be replaced by a constant K, and this constant is actually the modulus of subgrade reaction. It's mathematically you can say this K is a constant, but logically K varies with the reaction as well as the deflection. Now, if I try to find K, it's really simply K is equal to P over delta. So we can say the modulus of reaction is directly proportional to the reaction pressure and inversely proportional to the deflection. So if this deflection is more, conventionally the subgrade reaction will be less, or if the reaction is more will be the soil subgrade value. What will be the unit? This is a uniform distribution pressure. Obviously, pressure is the unit force upon unit area, and deflection is a depth, is a one dimension. So it can be anything of any unit. So if you look at the unit, that should be pound square inch per inch. It can be kilonewton per millimeter square per millimeter. It can be Newton millimeter square per meter. Any unit. Yes, for the sake of simplicity, we can say that it should be Newton meter square per meter, but actually it's not. Deflections cannot be in meters. Should be in micron meter, should be in millimeter. Because if the deflections are a meter, I'm sorry, this is no pavement. The pavement has failed long ago. Right? This is it. Now, other way of getting the unit is simply it will be pound per cubic inch or kilonewton per millimeter cube or kilometer per meter cube. Now the point is this will be the same unit of density, and we are not interested in knowing the density of the soil. We want to know the reaction of the soil. We want to know how much deflection is caused by each passing load. So it is better and it is logical to write the unit of modulus of corrosion in terms of kilonewton meter square per millimeter, or maybe pound square inch per inch. Let's move on. Now, how to calculate the modulus of reaction is an apparatus known as plate bearing test, or technique known as plate bearing test is conducted. This plate bearing test is similar to the pile load test you see while passing by when the bridge is being laid, the piles have been tested. So you can say it's a smaller version of what we do during the plate loading test in the say. We cannot categorize this as a laboratory test. It's a field test, though some of its requirement is also based in the laboratory test as well. But basically, it's a field test. So in what would you do? We do a compressive stress. We applied a compressive stress to the soil pavement layer through rigid plates of relative large size, and the deflections are measured at or for stress values. The exact loading deflection behavior of the soil for static load is applied by the bearing plate test. What are the apparatus? The bearing plates consist of a mild steel, 75 centimeter in diameter, and about 0.5 to 2.5 centimeter thickness. Other plates of smaller diameters use 60, 45, and 20 point centimeter are also used as a stiffener to the main plate. One of the way you can simulate this test is the way you have a different pavement layer. Obviously, you have a pavement layer, base layer, and then you have the binder layer, or you have a main surface layer. So these stiffeners are like this. And obviously, since we are talking about rigid pavement, there is no binder layer, there is a surface layer made of Portland cement concrete. Now, what are the loading equipment? It consists of a reaction frame and a hydraulic jack. The reaction frame may be loaded to give the needed reaction load on the plate. One more apparatus is the main apparatus. Actually, these are 3 or 4 dial gauges fixed on the periphery of the bearing plate. And that term frame should be supplied far from the loading area. This dial gauges must have an have a least count of say 0.001 inches, or they can be used. They can be linear vertical displacement transducers (LVDTs), so that the settlement, even a minor settlement, can be recorded. Let's look at the test setup. In order to conduct the test, we have to dig a trench that is normally 1 meter by 1 meter by 1 meter deep. And once you have a trench, you have to have a sand cushion, 1 inch maximum, to level the platform, to prepare a surface so that a horizontal surface, a level surface, so that the plate should be placed and other subsequent plates on that. So that this surface cushion, this sand layer, is needed to make the surface level. Then on the bottom plate, we can say at around 120 apart, 3 dial gauges are placed, and if you place 4 dial gauges, then they will be 90 apart along the periphery of the main plate. Okay. Then we have a frame, and this is a frame that is being rested on the ground and is obviously connected to the dial gauges. Over this plate, they have to be leveled again, so we have this support at both ends. And then we have on that plate, we have our hydraulic jack, and that hydraulic jack is connected with a probing ring, or we call a loading ring. And on the one side, and to the ball joint arrangement on the other side with a load reaction beam. So how this work? We apply a load from either from the truck or any other external loading to this beam. This beam presses this, now what we do, you just, what we do, we have a frame, reaction frame over there. We lift the jack through some deformation, and we note this loading values. This test is similar to what we have in the CBR test. If you look at CBR test, there's a frame all around, there is a probing ring, there is a jack, and obviously there are dial gauges, but obviously these dial gauges were here there is only here there are 3 or 4 dial gauges. There we have only 1 dial gauges. Also, the load is uniform. It's a single load, vertical load, one-dimensional load. So in this case, similarly, we lift this jack. So this is fixed reaction frame. We lift this jack around 0.25 mm increment, and we finish this test at the point. Most of the techniques are similar to what you do for the CBR test. This is the plan that shows the test setup. Now, so what you do? You prepare the site and remove the loose material so that 75 centimeter diameter plate rests horizontally on contact with the soil separator. We place the plate accurately, then apply the seating load so that the soil come in contact with the soil and release it once the um, plate gets seated on the soil sample. And at the same time, we make all the dial gauges set to 0 for a 0 load. What we do next is we apply the load by means of jack to cause an average settlement of 0.25 mm. And there's a rate of 0.025 mm per minute. And we need the load that is needed, and obviously the dial readings also noted. Then the average of the 3 or 4 settlement dial reading is taken on the average settlement of the plate corresponding to the applied load. Now we keep on increasing the load at each 0.25 mm with the same rate and noting down, and we finish this test at 1.75 millimeter. So conversely, this test is 70 minutes after the test setup is complete. Again, this test is similar to the CBR test, how it is there, the time and in terms of the increment, the load is taken, and there is a end of point that's like, for CBR, we stop at 0.5 inch penetration. This is the pictorial view of the experimental setup. The real pictures, you can see this is stiffener plate. The one is, completely intact with the soil, and then there are other size plate, and then the reaction beam, and from that there is an horizontal bar, and then for that, if you can look at those 2 horizontal bars, there are LVDTs that are being connected, or LVDT or dial gauges that are connected on the surface, and there is there's a reaction beam. This reaction beam can be of some vehicle, axle from the vehicle, and then there's a probing ring, and there's a load diameter, and there's a check. So how calculation is the same once you finish the experiment. you plot settlement and load on y-axis, settlement on x-axis and load on y-axis, and the pressure corresponding to 1.25 mm settlement is obtained from the graph. The modulus of subgrade reaction is calculated from the relation K is equal to P over 0.00125 kilometer per meter square pound meter. Oh, please forgive me for this kilometer per meter cube. This is how you can see this graph. Its load is a subgrade reaction, P over delta fraction, 0.12 in terms of centimeters. Obviously, it's then we'll have a sample recording sheet, which we mentioned soil type, the moisture content, the settlement dial, the plate diameter, area of the plate, prevailing calibration, the approximate settlement at every of this point at 0.25 mm, increment, right? And then the dial gauges, if there are 3 dial gauges, obviously, and or maybe 4 dial gauges, and to take average of these 4 values to get delta mm. And then you have these load dial values that is converted to equivalent load equivalent unit load by having by using the calibration factor supplied with this probing ring. And then obviously you find the modulus of variation by P upon 125 kilonewton per milliliter square per millimeter. Okay. Right. So what happens is that once you do this, once you do this, then this is not enough. What you do, once you take this reading, you have to correct it for 2 points, for 2 more measurements. One is the evaluating the value of modulus of subgrade reaction during subcondition. We all know that the reaction values of the soil become less when it is in soak conditions. The 2 samples are collected from the site. When you have completed the load test, one is subjected to a laboratory compression test under unsoaked condition, and the other in the soak condition. Pressure sustained by soil sample at different settlement is plotted in the similar manner and like the same graph, and you can calculate the improved modulus of subgrade reaction by using the modulus of subgrade reaction that you calculated previously during the field test and multiplying to the pressure needed for soak condition and the pressure load needed for the unsoaked condition. So this is the correction. You can use this value, this corrected value as input in a pavement design only when you have used a standard plate of 75 centimeter diameter. If you have not used the plate of standard plate, then you have to apply this value. You have to subject this value to one more correction, that is the plate correction due to the different size of the plate. Now what you do, we just have to heavy reaction load. Why we need it? Heavy reaction load is required for soil with K value and a plate diameter 75 is used for testing. If the reaction load is to be reduced, a plate of smaller diameter has to be used. So how would you do is, the correction is, you just know the corrected value. You have to multiplied with the ratio of the plate that is being used, that is used in this test, to the standard diameter. So this A is always 75, and this A1 can be 30, it can be 15 centimeter, whatever the plate you have used. So this will be now the correct value that will be used in the pavement design. Now, how this data is recorded, how data look like, or you can say as an example problem. So what you do, the serial number 1, 2, 3, 4, 5, 7, 8 corresponds to the settlement at 0.25 mm as shown in the table. And from that, for each of the settlement, you get this value of probing ring. You've converted this probing ring into a load, unit load, by using a calibration factor. So this is how you have obtained. And then you have reading from A, B, C, where you have taken the average of the settlement in this column. So what you do in real sense, this is known to me. This is measured in the field. This is measured in the field, and A, B, C are measured. The other, this column, the column, this one, this column, and these columns are the derived column, obviously from the data from the left. So once you come up this data, you plot every value on x-axis and the load values on the y-axis like this. Have a best fit curve, obviously. And for corresponding to 1.25 mm settlement, you get the value, load value of 5.5, or in other words, 4.4 kilonewton per millimeter square per meter is the value of subgrade reaction. Now, if you don't have any test apparatus, don't set up, don't get disappointed. You can always use the CBR values to know your subgrade reaction. Simply multiply 1500 into CBR, divide by 26 to 0.7788. So this is how subgrade reaction of the soil is measured and calculated, and this is used for further design as a value, input value for the pavement design. So that's it for this lecture. Thank you very much for your listening, and